been there for the whole time? Okay. Okay. So I should probably view the chat. So that is hidden afterwards. I think should go away, right? Okay, good. And hide the pointer on my screen. Okay. So, and now I have to press here too. Okay. So we'll now construct a lattice model which evaluates all Schur polynomials. As I mentioned, we will then build on this model later on in the talk. This initial lattice model will be constructing by a simple rewrite of the known combinatorial description. But this is not a luxury. So the combinatorial description of the Schur polynomials in terms of Young tableaus, that's not a luxury we have in our papers, where we instead use the solvability of the model to compute the Whittaker functions. So the lattice model consists of a grid, a two-dimensional grid with R rows, sufficiently many columns for what you want to do, and where each vertex has 4 adjacent edges, even the ones on the boundary. And we will assign data to these edges according to certain rules. And in this initial example, the edges will be either filled in, drawn in bold, or they will not be filled in. And because of these rules, the edges form paths in the grid. And for given boundary conditions, there's a finite number of configurations, which we call states. A state S is assigned a Boltzmann weight, which beta, which is a polynomial in R complex variables, Z, one for each row, numbered like this. The partition function given some boundary conditions is then defined as the sum over all such states with given boundary conditions over these Boltzmann weights of the states. Thus, the partition function is specified by the boundary conditions, the rules stating which configurations are admissible, and the weights for these configurations. And the goal is now to specify these 3 things such that any Schur polynomial is equal to such a partition function. So the Schur polynomials are defined like this. So we let lambda be a partition of R, which we seen as a list of integers paired with zeros on the right until it's of length R. We define the associated Schur polynomial as the ratio of these determinants here. And by the properties of the determinants, this is actually a polynomial, and it is symmetric in the variable z. That it is a polynomial is perhaps easier to see in the combinatorial description using semi-standard Young tableaus. Shape lambda looks like this. And the semi-standard Young tableaus are obtained by taking a Young diagram of shape lambda, and then we fill in numbers from 1 to R, such that the columns are, the rows are weakly increasing and the columns are strictly increasing. And here the weight of the tableau is the number of ones, number of twos, number of threes, etc. So there is a bijection between the semi-standard Young tableaus and certain southeast moving lattice paths. Let me show you how. We start by numbering the columns from right to left. Then we define lambda I of t to be the shape of t after removing labels larger than I. So in the first case, we recover the shape lambda again. The next, we remove the box with 3 to get shape 1, 1. And then lastly, we're left with just a single box shape 1. Now, these will list the columns which will be filled in each row, but to avoid overlaps, we add row, this vector here, to each item. And the resulting column numbers shown here form what is called a Gelfand-Setlin pattern. And the paths are now determined by filling in these columns 4 to 0, 2, 1, and 1, and the rest is determined by that. So here, the paths enter the top boundary and an exit on the right boundary. And we notice that each vertex comes in one of 5 different configurations with its 4 adjacent edges. And the bijection between semi-standard Young tableaus of shape lambda are to these lattice paths using these 5 different vertex configurations, where we fill in the top boundary with edges as column lambda plus rho. The goal is now to imitate this form here for the Schur polynomial using lattice model data. So we know that the weight of T essentially counts the number of filled in edges, or left edges in each row. And we achieve this goal by assigning a Boltzmann weight to each vertex, which will depend on row parameters Zi at each row. And here we see we add these weights up here, a weight Zi for every left edge that is filled in. Then the Boltzmann state for the whole, Boltzmann weight for the whole state is the product of these vertex weights. And for example, here, see if I can paint this. We have, for this state example here, we have 1, 2, 3 left edges on the first row. So we have Z1, 2, 3, 2 on the second row, and 1 on the third row. So that's why it looks like this. It's not difficult to show that in general, we get that the weight of a state equals this here, where W0 here is reversing the orders of parameter Z. Now, if we take the full partition function, we sum over all these cases, and we do indeed get our Schur polynomial back, where we can remove this W0 by remembering that it is symmetric in the variable Z. So this is how we get a partition function computing all the Schur polynomials for us. Any questions so far? I see the cat is leaving. So let us show how this is useful. By proving the dual or second Cauchy identity for Schur polynomials. This is, of course, already known, but let's see. It's a simple example to show how this works. In the process, we'll also upgrade our lattice models from having 5 different vertex configurations to something having 6 vertex configurations. So the Cauchy identity for Schur polynomial looks like this. If it looks a bit off to you, it's an equivalent formulation of the standard dual Cauchy identity, which you can find in McDonald, his book. Here, lambda hat is the complement of lambda, which you get by completing the box and then rotating 180 degrees like this. And then prime is taking the transpose of the conjugate, which you obtain by flipping it in this axis like that. Now, to prove the Cauchy identity using the lattice model, we will use the symmetry of the vertex configurations. And this symmetry is most easily seen if we rewrite them in a different notation using arrows, and which is, by the way, the standard way physicists like to draw these configurations. So we start by this standard configuration here of arrows pointing in these directions. And every time we have a filled in edge, we reverse the arrow. That's how you go between the 2 different drawings. And we see that if we flip this vertex here in the horizontal line, then this one goes to that one, this one goes to itself, this one to itself. There's one missing. So we add that one here. And looking back, it's filled in edges up at the top like that. So that was a missing configuration. Now we're up to 6 vertex configurations. And we introduce a parameter v for this weight here. We'll actually put minus v here. And we also adjust this weight over here to include a minus v as well. And this is for solvability. We have to adjust that one. It needs to satisfy a Yang-Baxter equation. So adding these adjustments, these new weights, the minus v, this introduces slight deformation of the partition function. This looks like this extra factor here. And we note that we recover our lattice model from before by taking v equal to 0. But we also note that if v is -1, the Boltzmann weights are invariant under such a flip. And this is what we'll need to prove the Cauchy identity. We start by considering a large system with the following boundary conditions, where we fill in the top and the right boundaries. We also label the rows a little bit differently, like this. The partition function is then summed over all the admissible states, and it's straightforward to compute that partition function, which are labeled by z, x, y here. Now the trick is to cut this lattice model into two, a top and a bottom part. And at the cut of the middle here, for all admissible states, there will be two edges somewhere at the cut going down to the bottom half. And this is because we have 4 incoming at the top, 2 exiting here on the right at the top. There will need to be 2 exiting on the bottom as well. So we have these different edges, but we need to, they can appear not only at the places I've drawn them, but all the different possibilities. So we have to sum over this, and we will label the places of the edges by lambda. So when we sum over different states in the partition function, we sum over lambda as well. Now we group the states which have the same lambda and form a partition function for the top and bottom by summing over these states. And the original partition function is then recovered like this. The bottom partition function looks exactly like we had before. It's a Schur polynomial. The bottom part, the top part, we have to massage for a little bit. We flip it, which we remember if we have v equals -1 preserves the partition function. So what happens then is that the lambda here, which is originally at the bottom, goes to the top and becomes lambda hat conjugate. And when we put v equals to -1, this becomes exactly the Cauchy identity. So this concludes the study of our first toy lattice models. Are there any questions before I continue defining Whittaker functions? So this deformed partition functions is actually secretly a Whittaker function. So let me define what I mean by Whittaker functions. The details will not be so important, but if you're interested, I kindly ask you to look at the papers. Here I will only give at least an overview of the objects that we will study. So the lattice model we construct are for the general linear groups, but the representation theoretical results in our papers hold for any reductive group, but let's just keep to GLR here. In this talk, I will also restrict to the p-adic numbers P instead of any non-archimedean local field. E is the Borel subgroup of all upper triangle matrices and its subgroup with unit diagonal. And we let psi be a generic character on N, which we, similar to Steve talks yesterday, we will later take to be a standard character. Then a Whittaker model is an embedding of an irreducible representation into this induced representation of psi from n to d, which are functions on d to the complex numbers, which transform by a psi n when we translate with an element in n. Yes, exactly. There's some smoothness and compactness as well. Thank you very much. So, a Whittaker function is then an element of this image of the Whittaker model. And to say which Whittaker functions I study, I need to tell you two things. First, representation, and then an embedding. But let's start with an embedding. We take a canonical one, which is this integral here over n. And it's the same Jacquet integral that we saw in Steve's talk yesterday, but here now over the p-adic numbers instead. In fact, this is also isomorphic, unique up to isomorphism if it exists. Now, I also need to tell you the representation, which we take to be the unramified principal series representation, pi z, which is specified by our complex number z. The details of this representation, how to construct, is shown in blue here, but it's not going to be important for this talk. There is a unique spherical vector, though, up to normalization in this pi z, which we called f circ. By this, I mean that it's right invariant under the maximum compact subgroup. The associated spherical Whittaker function, if we take curly w psi of this f circ, is determined by its values on the diagonal. P lambda was defined in blue up there. Lambda is a tuple of integers. And this can be computed by the Casamontian-Leica formula as this while deformed by the denominator times character on the dual group, which here is just the Schur polynomial. Oh, thank you very much. Thank you. I should add that. Thank you. Note in particular that this is exactly our partition function if we put p equals to p inverse the prime p. And that we had a discrete set of data for the argument specifying the values of the Whittaker function. So this was the spherical case. Let us generalize. There are several different generalizations we may do. So if we let this circle here denote the spherical vector for GLR that we saw in the previous slides, then Kasselman and several others realized that if you want to, even if you only want to compute the spherical Whittaker functions, it is very useful to refine this, split it up into several terms, having a richer representation theoretical structure. And these are the Iwahori-Whittaker functions shown here, which are instead invariant under a smaller Iwahori subgroup to be defined in the next slides. And we studied the corresponding lattice models in papers 1 and 2. There's another generalization which is important to number theory, where we instead go to a metaplectic cover, G tilde, of the underlying group. And this was the first models for the spherical vectors were constructed by Brubaker, Baumschinter, Friedberg, and Gallons. And in paper 3, we combine these two generalizations into an exhaustive lattice model, including all of these cases as subcases. The Iwahori-metaplectic duality is then a duality between those objects over here, which we discuss and show in paper 4. And they are a priori completely different objects. On one side, we have Iwahori fixed vectors for the reductive group. And on the other side, we have spherical vectors, but for a metaplectic cover of the group. So let us now define these different objects in blue in the next slides, starting with this representation theoretical generalization. So the spherical case was, the spherical vector was obtained by taking something that was invariant, right invariant under the maximum compact subgroup. Note that the group G can be decomposed into B times K like this. And the spherical vector is unique up to normalization. The Iwahori-Whittaker function is instead obtained by taking something that is right invariant under the Iwahori subgroup, which is a subgroup of K, which is lower triangular mod P for GLR. And now the group G can be decomposed into this disjoint union here, union over wild group elements like this. And we get a basis of Iwahori fixed vectors enumerated by the wild group W, permutation of SR. The spherical vector can be expressed as a sum over these refined Iwahori vectors. Each of those is supported only in one piece of the union. On the lattice model side, this corresponds to assigning different colors to the paths we saw before, thus making the paths distinct. Schematically, the partition functions will then go from being spherical Whittaker functions to Iwahori-Whittaker functions when we add the colors for the model in paper 2, which was the 6 vertex models, that is with V non-zero. Similar for paper 1, if we do the same with a 5 vertex model, we go from Schur polynomial to something called de mesure atoms. So this is what happens if we assign a different color to each of the paths. What happens if we have a repetition of some but not all colors? In that case, we get something called parahoric-Whittaker functions in paper 2. And in paper 1, we get de mesure characters. But I will not be able to talk about this much further. So in more detail, we introduce a palette of colors, which we assign an ordering like this. We then take the state of the previous model and start adding colors to the different paths, starting on the top boundary with R, B, and G. Now, we note that there are different ways of coloring the same paths, even if we restrict to a particular order for the right boundary, like we see here. So this means that the partition function for the color model sums over more configurations than before. And as I mentioned, we get a new boundary data and the permutation of the colors on the right boundary. We have constructed a vertex configuration weights such that the uncolored partition function is refined to a sum over these colored partition functions. So we have to be careful how we define these Boltzmann weights for each possible vertex we can see in the colored version. So in paper 1, we show that we get the de mesure atom. Paper 2, we get the Iwahori-Whittaker function, and we see that there is a bijection of data as well. So for paper 1, there's actually a bijection between the states of the model and so-called crystal de mesure atoms. But here in paper 2, as I advertised, we have between the boundary data of the lattice model and the data specifying the Whittaker function values. The extra structure that is obtained by introducing colors also allows us to write recurrence relations of the partition functions. More specifically, that is also how we compute them. These recurrence relations They follow from Yang-Baxter equations, the solvability of the underlying for the underlying quantum group. And specifically, the partition function is expressed as a sequence of divided difference operator of Demosier type acting on this monomial here. So the details are not important how these operators act, but rather that we have such an expression. These are actually the same recurrence relations found for Whittaker functions, Brubaker Brumplicata, and this is how we show that the partition functions equal Whittaker functions. There's a hint to what comes next. We do the same for the metaplectic case in paper 3, where we compare with what is known for metaplectic Whittaker functions from Chintaganos, Puskás, and Patnaik Puskás. So this is my segue to the metaplectic groups. Are there any questions so far? Yes, please.
Could you comment about that?
Right. So we know. So when we constructed the weights for the lattice. Oh yeah, I don't need the mic. Sorry. So Sol asked. It looks like in our paper that we construct the weights first and then get the underlying quantum group, and that is correct. So what we do is that we find weights which satisfy a Yang-Baxter equation for some R matrix. And then we see, oh, this R matrix is exactly coming from this quantum group, GQ, GL, in this case, 1R hat. Now, the hope is in the future, and what we're working on right now, is that we will go the other way. We start with the quantum group, and we tell you the modules involved for the edges, and then the weights will fall out. But that is to be done. That's what we're working on right now. Thank you, Sol, for mentioning that. Great. So we will now talk about this other generalization, where we go from the group GLR to a metaplectic cover, an N cover. And this is a central extension by the group of nth roots of unity, and can be seen as a generalization of the standard double cover of SP2N, which I think we saw in some earlier talks. We talked about metaplectic covers. Was it perhaps your talk, so don't remember. The principal series is defined similarly, but now we get vector valued representations. So they are n to the R dimensional instead of one dimensional as before. This can hand-wavily be seen as follows. So in the standard GLR case, non-metaplectic case, the torus, which we start our induction from, is abelian. So of course, it's irreducible representation at dimension 1. But for the metaplectic case, the pre-image of the torus, T tilde in the metaplectic group, is not abelian. And the quotient T tilde of the maximal abelian subgroup is isomorphic to Z over NZ to the R. So that's how we get N to the R different cases. So we get the Whittaker module is no longer unique. We have to project to one of these components, sigma, in this Z over NZ to the R. So there are N to the R metaplectic spherical Whittaker functions because of that. And often in the literature, one often considers not the separate components, but a sigma average, for example, in these papers here. But we showed in paper 3 that this is actually not the description at all, since one can easily recover the different sigma components from the sigma average. So now let me briefly mention some connections to number theory. As advertised, I want to say true to the theme of the workshop of connecting physics and number theory. So here we have lattice models I want to connect to number theory now. So as we know, the spherical Whittaker functions are local components of Fourier Whittaker coefficients of global spherical algorithmic forms. So what do I mean by that? for the reductive case, the non-metaplectic case, the Fourier coefficients, they factorize as an Euler product over the primes of these Whittaker functions because of uniqueness of the Whittaker functions. But for the metaplectic case, things get a bit more complicated. And they do not in general factorize like this Euler product here, but the coefficients satisfy something called a twisted multiplicativity that involves Gauss sums or nth power residue symbols. The coefficients are determined by their so-called p parts, which are a p power, a generating function of p power coefficients. And these are metaplectic spherical Whittaker functions. And the p parts are also used for constructing wide group multiple Dirichlet series, and together with their applications to L functions have been extensively studied in a lot of papers as shown here. But we will not talk directly about the lattice model for this case, but we'll skip that for now and directly describe a lattice model for this more general case where we combine the two generalizations. And of course, we'll see how we can recover that one as a subcase. Here I've also summarized the different dimension of the space of Whittaker functions. So we have spherical one-dimensional, spherical metaplectics n to the r. Now remember the Iwahori basis vectors were enumerated by the wide group, so we have r primes, r factorial dimensions there, and here we combine the two to this. So the lattice model for the bottom objects we construct by having two sets of R paths, which we assign colors from two different palettes. As before, we have a palette of R colors, each assigned to southeast moving path without repetitions. We also have a palette of size n of what we call supercolors, and each assigned to a southeast moving path, possibly with repetitions as shown in the example. We'll draw these as dotted paths. Besides the usual boundary data for the Iwahori basis, W, and the group argument on the top, specifying that boundary condition, we also get the boundary condition on the left, which signifies the Whittaker model by this component sigma. We then show in paper 3 that the partition function computes all the values of this metaplectic Iwahori-Whittaker function. And we also get a bijection of the boundary data and the Whittaker function data. Furthermore, we show that if we sum over some color permutations, that amounts to equating colors in the model. And to obtain the metaplectic spherical function, all we have to do is to equate all the colors, thus summing over all the W's. And when we do that, you can notice that the paths, which would all now be of the same color, are superfluous. So we can remove them. And we see that this is very similar, the spherical, the lattice model for spherical metaplectic Whittaker functions we get are very similar to the regularly colored ones we had for Iwahori non-metaplectic Whittaker functions. And this leads us to the Iwahori-metaplectic duality. So this is a relationship between these two objects as advertised. And we show in paper 4 that the associated lattice models are actually part of the same parametric family of lattice models, which are related by so-called Drinfeld twists of the underlying group, quantum group. More specifically, if we let the spherical metaplectic Whittaker functions be denoted by phi tilde sigma over there, and phi w for the Iwahori non-metaplectic ones, we get that if the parts of sigma are distinct, then this one equals the spherical metaplectic equals some Gauss-sums times the Iwahori-Whittaker non-metaplectic Iwahori-Whittaker function on the nose, with the change of the row parameter, Langlands parameter z, from z to the n. On the other hand, if we take all parts of sigma to be the same, then we get that it's exactly a non-metaplectic spherical function on the nose, like this. And based on these two extremal cases, and also the schematic lattice model argument given on the next slide, one can conjecture that in general, these spherical metaplectic Whittaker functions are actually non-metaplectic parahoric Whittaker functions with the right insertions of Gauss-sums. So more or less equal if we insert the right Gauss-sums. So let me show you what the idea is behind that statement. We start with the metaplectic spherical model. Remember, this was the model with only the supercolored paths, the dashed paths. And we apply what is called the gamma delta correspondence, which is a highly non-trivial identity on the level of partition functions, and not for individual states, but essentially gives us southeast moving paths instead of southwest moving paths. And it looks very much like the Iwahori model if we replace the supercolors by regular colors and at the same time change the Boltzmann weights from having Gauss-sums in this case to not having Gauss-sums here by a Drinfeld twist. And that's how we get the non-metaplectic Iwahori. And we see that if we have duplicate, a repetition of supercolors here, we get a repetition of regular colors here. And as I mentioned briefly earlier in the talk, this gives us a parahoric Whittaker function if we have repetition of some colors, but not all. So there's also a representation theoretical version of this argument using De Maizière operators. So to summarize, we have constructed lattice models whose partition functions compute all values of the various Whittaker functions shown here. And motivated by these lattice model interpretations, we also see a duality between two objects, the spherical metaplectic and the non-metaplectic Iwahori, which a priori seem to be very different objects, but now shown are related. So I will end this talk by showing a list of other results from the papers, which I will not be able to talk about today, but show the many different connections we get to various other areas of mathematics using these lattice model interpretations. We get, for example, Cauchy identities for the metaplectic spherical Whittaker functions. We get partition functions for quantum Fock space vertex operators in papers 0 and 4. We also compute all values of our Iwahori-Whittaker functions, not only on the torus arguments. People who are mostly interested in spherical Whittaker functions only need to worry about torus arguments, but we computed all the different values. And we also showed, as I say, that even if you take the sigma average, it's easy to recover any of the sigma components. We also show that these parahoric Whittaker functions in general are McDonald polynomials in a certain limit with prescribed symmetry. And in particular, the Iwahori ones are the non-symmetric McDonald polynomials. We also find algorithms for computing Lesko-Schützenberry keys of interest in combinatorics in paper 1. And we can have a new way of constructing lattice models via fusion of vertices. And that's how we get the Boltzmann weights for the colored models. Thank you very much, and I will not keep you from the coffee.
Thank you very much, Henrik. So we have time for questions. There's one over there. Let me go there. And I think there will also be something on Zoom, if I see correctly.
So thank you. I wanted to say, first of all, I think this is just a beautiful body of work. You've really accomplished a lot by doing all these constructions, and it's really exciting to see it.
Thank you.
I do have a question about this duality. So I saw z going to z to the n in the Langlands parameters, and that's very reminiscent of the Shimura correspondence. Gordon Savin has a paper on local Shimura correspondences from something like 25 years ago. Do you see a connection to that work?
I remember we talked about something like that, but I don't remember if we had any conclusion. But it's a very interesting thing to look at, definitely, and we should talk some more about that.
Okay, great. And my other question is, of course, there are other kinds of ice that capture other split reductive groups. Are there similar results for some of those, or is that work in progress?
So that's not something we have considered right now. We have mainly focused on type A. But as you mentioned, there are lattice models for other types, other reductive groups. I'm not sure if any of perhaps Dan or Ben's students might be looking at something like that. I think I've heard that been mentioned, but nothing we are looking at the moment. Thank you.
Thank you. For some reason, I can't see the chat on my computer, so I don't know what this message is about.
Let's see.
But if there's a question from Zoom, the person may just unmute themselves and ask the question.
I can't find the cursor now. I'm sorry, I can't see the chat either.
There's a question from Eyal. Maybe Eyal, just go ahead, unmute yourself. I think we should be able to hear you.
Okay, thank you. Hi, Henrik.
Hi.
I'd like to ask, in the linear case, results on spherical Whittaker functions are usually based on uniqueness. For example, going back to Kasselman and Shalaika's original proof, do you see or use uniqueness at all in the physics picture?
I'm sorry, I didn't hear the very last part. It's very low, the volume in here.
My question was, do you see or use uniqueness when you consider the physics picture? I know there's no uniqueness in the metaplectic case
right.
either, but
so there's a question about uniqueness of the model. So there, as you mentioned, in the metaplectic case, there's not a uniqueness for the Whittaker models. And as we see, this corresponds to having several different boundary conditions on the left with this sigma. So this is not something we have to assume that there's only one particular case of sigma that we look at, but we look at all the different possibilities of these components to be able to get a recurrence formula for the partition functions. We use all the sigmas. Does that answer your question?
Well, okay, so, but in the linear case, we do have uniqueness, and the models also apply to the linear case. Do you see that at all in?
In the lattice model side, do we see any hint of the fact that in the linear case that there is a uniqueness of the Whittaker model?
Yes.
Let me think. Is that a correct interpretation of the question first?
Yes, thank you,
Yes, thank you. Let me think. Yes, so it would correspond to taking n equals to 1, and that would leave us only with a single supercolor. So in the same way that we had for the colors that they were superfluous when we had them all to be the same, it will be the same here, that we would have only one supercolor, and the dotted paths we can just remove them. So there's some hint of uniqueness being shown there, that they're superfluous when we draw a dotted path for n equals to 1. But other than that, I'm not sure how to see uniqueness in the linear case.
I see. Thank you. That answers my question.
Thank you.
Thank you. Are there more questions? Maybe I can just use the opportunity to ask. So when you talk about the super colors, I remember in previous talks on the topic that I've been to, there were super algebras. I mean, is there in relation?
Excellent question. Thank you. Yes, so I haven't mentioned what the quantum groups are that appear in our models, but the fact is that for the most general case, with general N and general R, where or for the Iwahori case and for the general metaplectic case, the underlying quantum group is UQGLN pipe R hat, which means that this is a superalgebra. And in particular, this means that the colors are associated to the even part of this superalgebra and the supercolors to the odd part. So that's why we name them colors and supercolors. And we do see that this duality of Iwahori-metaplectic, this metaplectic Iwahori duality is some kind of symmetry between colors and supercolors. So that is also tantalizing, I think, as a physicist.
Yeah. Okay, thank you. So, yeah, I don't see any other question right now. So let's thank Henrik again and take all other questions to coffee.
Thank you very much.
And we start again at 11:15.